Hello and welcome to GB440, our lesson on Chapter 12, Linear Regression and Correlation. This is the second half of the chapter. So, if you remember in our last class, what we did is we started looking at the relationship between two variables. And we would take two variables, we'd have to figure out which one was the dependent variable, which one was the independent variable. The dependent variable went onto our y-axis, so it became our y values, and our independent variable was on our x-axis and became our x values. Then we created a scatter diagram to plot our points, and then in Excel, we added in a trend line, and then we displayed the equation for that trend line right on our chart, and we later learned that that equation is the equation for our linear regression equation. So we were then able to go through and use that equation to predict what our dependent variable should be for any value of x. So let's get rolling today. Chapter 12, Linear Regression and Correlation. As I was saying, last lesson, we differentiated between dependent and independent variables. Then we applied regression analysis to estimate the linear relationship between two variables. And we did that with the scatter plot diagram and the trend line. The trend line, when we displayed the equation, that was the equation for a linear regression. So that brought us into evaluating a regression equation to predict the dependent variable for a certain given value of our independent variable. So today we're going to calculate the standard error of the estimate, coefficient of determination, and correlation coefficient. And we're going to create a regression analysis table using Excel. So you'll want to make sure you've got your Chapter 12 data files Excel file open. Remember our two examples. We've got the Canadian Basketball League, where we're looking at the relationship between players' heights and number of baskets made. And then our other examples, the copier sales example, where we're looking at the relationship between the number of sales calls made and the number of copiers sold. So, in the previous lesson, we learned how to create a scatter diagram and insert a trend line and linear regression equation. Now we will explore how related these variables, for a basketball example, the heights of the players and baskets made, how related those variables are. And we're going to do that by exploring the standard error of the estimate, correlation coefficient, and the coefficient of determination. So the good news is, when we create our regression analysis table in Excel, we'll have all of this data already displayed. We just have to find it and then interpret it. So we'll start off with the standard error of the estimate. The standard error of the estimate, or SE, measures the scatter or dispersion of the observed values around the linear regression equation, or the trend line. It's similar to the standard deviation in that it's based on squared deviations. The sum of the squared deviations is the least square value used to find the best fitting regression line. So Excel's already done this for us when we went and we created our scatter diagram and inserted the trend line. It was using the sum of squared deviations to find the least square value for that line. And the denominator for the standard error of the estimate is n minus 2. And this is because we've got two variables we're looking at, so we have to subtract 2 degrees of freedom, one for each variable. Good news is we're not going to have to use that equation. So the standard error of the estimate, SE, is the typical vertical distance or average vertical distance of the observation from the linear regression equation. So in the previous example involving the Canadian basketball players, we examined the variables of players' heights and the number of baskets they made. We found the linear regression equation to be y prime equals 0.3848x minus 11.443. Remember, 0.3848, that's our slope, and negative 11.443, that's our y-intercept. What we now want to know is how accurate is this equation and how strong is the relationship between a player's height and the number of baskets they made. And so we're going to start exploring that. So first up, we're going to use our Canadian Basketball League example, and we want to know what is the standard error of the estimate. So we're going to do Excel for this, but remember our last class, we created a scatter diagram after figuring out that number of baskets made was our dependent variable and the height of the players was our independent variable. So we put our dependent variable on our vertical y-axis, independent variable on our x or horizontal axis, and then we created a scatter diagram, inserted a trend line, and displayed the equation. So our equation's right there. Now we're going to go over to Excel. So I'm just going to flip to Excel quickly. All right. So now you can see we've got our Canadian Basketball League example in Excel. And in order for us to go and do a regression analysis, it's going to be very similar to when we went and we did the NOVA single factor analysis in Excel. So we're going to go up to the top and we're going to go across until we find our data menu. There's our data menu right there. We're going to click on that. And then we've got to find data analysis. On mine, that is way over to the right. When we get data analysis, we're just going to click on that. And we're going to have to scroll down. Everything's in alphabetical order. We're looking for regression. So there it is right there. Select regression, then click OK. It's going to bring up a dialog box. So the first thing we have to do is we have to input our Y range. This is just asking, hey, where is the data for Y? So remember, Y's are dependent variable. And in this example, that's number of baskets. So we're going to click the little arrow beside the input box there. Brings us back to Excel. We're going to grab number of baskets and all that data. We can keep our labels there. So once we've done that, it's all selected. We go back to the little arrow, press that again. It'll bring us to our dialog box. Perfect. Should now see C3 through C15 was selected. Now we're going to do the same thing for our X values. So once again, we'll press on the arrow, go back to Excel. This time we're going to grab the player's heights. So labels and all the data. Perfect. Now we're going to hit the down arrow. Return back to our dialog box. And so now we've got our Y values and X values both in there. If you selected the labels, make sure you check off the box for labels. We don't have to worry about the box that says constant is 0. Leave that unchecked. Same thing with confidence interval. We're not dealing with that, so we can leave that unchecked. Residuals is always a good piece of information to have. We won't be looking at it in this class, but always good to put in if you're doing a regression analysis. Output options, we can either output this onto a new worksheet, but in this example, I'm going to put it right on the same worksheet. So I'll hit output range, hit my arrow beside the input box there, and just select where I want my regression analysis to start. So I'm going to say cell A17 here. Click the downward arrow. Perfect. We've got everything in there. Now all we have to do is hit OK. And you're going to see Excel creates a lot of information for us here. So we have a lot of information. I'm now going to go through and show you what pieces we need. But once we've created this table, we have all the information we need for today's lesson. So we've inputted this, or we created this table. I'm going to flip back to PowerPoint and just guide you through where everything is and what it means. So here's the steps on how we created our regression analysis table. So in the Basketball Heights worksheet, go to the data menu, select data analysis, scroll down until you find regression, press OK. Make sure you insert your data for Y and X. If you've included labels in your data, make sure you select labels and check off that box. Checking off the box called residuals, as I said, always a good idea, although we won't go into it in this class. And then select the output option you want, press OK. So this is what our input should look like right before we hit OK. Then we're going to hit OK. We get our charts, and we can see there's a lot of information here. Right near the top under regression statistics, that's where our focus will be. So our standard error, the estimate, it's just called standard error in Excel. And we can see it's 1.893762,759. So for our basketball example, from the regression analysis, we can see that the standard error, the estimate is 1.89. So this means that the average distance between the actual data and the predicted data deviates by 1.89 baskets. Note as well, we can also find our y-intercept and slope from our linear regression equation in our regression analysis table. Our intercept is right there, negative 11.4427. We rounded that up to negative 11.443. And then height in inches, that's our slope. In this case, 0.3848. So those two values, if we just look back at our equation quickly, you can see our slope 0.3848 times x and minus 11.443. So we don't have to create the scatter diagram if we don't want to find out what our linear regression equation is. We can just do the linear regression analysis table and find the intercept and the slope right from that if we want. All right, so we looked at standard error of the estimate for the basketball example. I'm going to recommend you pause the video here and just try and see if you can create that table for the copier sales example and figure out what the standard error of the estimate is. All right, hopefully you've had a chance to create the regression analysis table for this example, and you've had a chance to find out what the standard error of the estimate is. This was what we did in the last class. We created our scatter diagram, inserted the trend line, and then added in the linear regression equation. Now we go and we create the regression analysis table. And the first piece of data we'll grab is our standard error. And our standard error in this case should have been 9.900824. We're just going to round that to two decimals. So the standard error of the estimate is 9.90. So on average, the actual data deviates 9.90 from the predicted data, or deviates 9.90 from the linear regression equation. So our copier sales, on average, deviates 9.9 sales away from our linear regression equation and our trend line. So the standard error of the estimate tells us how much deviation there is from the actual data to the regression line, but we still want to investigate the strength of the relationship between the two variables we're investigating. Also, it is possible that the relationship between two variables is just purely coincidental and that the two variables just happen to trend in the same direction. So, we want some more information about the strength and whether those two variables are actually related. So, to start off with, we're going to look at the correlation coefficient. So, correlation analysis is a group of techniques to measure the strength of the association between two variables. And in order to do this, we'll need interval level or ratio level data. So, if we have interval level or ratio level data, then we can go through and we can do the correlation analysis. And the sample coefficient of correlation, or correlation coefficient, is identified by the lowercase letter r, and it can assume a range from -1 all the way to +1. Values of -1 or +1 indicate perfect and strong correlation. The closer the value is to 0, the weaker the correlation or weaker the relationship between the two variables. If we get a negative value, it indicates an inverse relationship, and positive values indicate a direct relationship. So if we get a negative value, we're going to get a downward sloping line. And if we have a positive value, we'll get a positive sloping line. So, two examples of what perfect correlation looks like. If our correlation coefficient, R, equals -1.0, that indicates perfect negative correlation. So we get a downward sloping line. So as x gets bigger, y actually gets smaller. And if it's -1.0, that means perfect correlation. So all our estimated points, or sorry, all our actual points lie right on our linear regression equation. Over here, if we got an R value of +1, so our correlation coefficient is +1, that indicates perfect positive correlation. So we get an upward sloping line as x increases, so does y. And all our actual data will actually line up perfectly on our linear regression equation or trend line. Perfect correlation doesn't happen often in the real world. Normally, there's some deviation from our linear regression equation, um, but those are just examples if we did have perfect correlation. So here we've got three diagrams of varying strengths. The first one is an R of 0, which means there's no correlation between the data. And you can see here number of children versus annual income. Um, in our scatter diagram, we're going to see our points are all over the place. And when we put in our trend line, it doesn't really show a relationship, and the points are really, really far from it. So in this case, no correlation. our correlation coefficient is 0. Here's one where our um, correlation coefficient is negative, and it's a weak negative correlation. So we may get an R value here of like -3, -3.5, somewhere around there. Even lower than that, we can see that the data generally does trend downward. So as X increases, our Y does tend to decrease, but there's a lot of deviation from the points to our actual linear regression equation or trend line. So this is a weak negative correlation. And then over here, we've got a strong positive correlation, and we can see all the points are clustered really close around our trend line or linear regression equation. In this example, our R value might be 0.8, 0.9. It's getting close to that +1 value, not quite on it, or all the points would be right on our linear regression line. So when you do calculate out your correlation coefficient, or you create the regression analysis table in Excel and you see your correlation coefficient, if you want to interpret it, slide 22, which is our next slide, is a very important slide to go to. This will guide you. So the correlation or coefficient of correlation or correlation coefficient is a measure of the strength of the linear relationship between two variables. And it also tells us direction. Positive value means positive correlation. A negative value means negative correlation. And we can see if we're at 0, we have no correlation. And then as we deviate a little bit from 0, so as we get to say 0.25, we have a weak positive correlation. At 0.5, we now have a moderate positive correlation. Somewhere around 0.75, we have a strong positive correlation. And then, of course, at 1, we've got a perfect positive correlation. And the negative side is a mirror image of the positive side. It just indicates that we've got an inverse relationship, so our correlation's negative. But same thing, negative 0.25, weak negative correlation, negative 0.5, moderate negative correlation, negative 0.75, strong negative correlation, and the closer we get to -1, the stronger that negative correlation is. So that's a great slide for you to go to interpret the results that you get. All right. So let's take a look at the characteristics of a correlation coefficient, kind of sum it all up, and then we'll look for it using our examples. So the sample coefficient of correlation is identified by the lowercase letter r, and it shows the direction and strength of the linear or straight line relationship between two interval or ratio scale variables. Ranges from -1 up to and including +1. A value near 0 indicates there's little association between the variables. A value near 1 indicates a direct or positive association between the variables. A value near -1 indicates inverse or negative association between the variables. So let's go back to our Canada Basketball League example here. So we're going to go back to our chart. We're going to identify the correlation of coefficient, and then we're going to actually interpret it. So just a friendly reminder, data analysis, go to regression. This is what your input should be for your regression table. You'll click OK and poof, We get our correlation, or sorry, our linear regression analysis table. And now what we're going to do is we're going to go down just below regression statistics. So the same area where we found our standard error. Above that, our first option is called multiple R, and that's actually our correlation coefficient. So in this case, our correlation coefficient is 0.905. Correlation is positive 0.905, really close to 1, so it's indicating a very strong positive relationship between the player's height and how many baskets they made. In our copier sales example, we're going to do the exact same thing. So pause the video, go back to your copier sales data sheet, take a look at your table, find out what is the correlation coefficient, and see if you can interpret the strength of the relationship. All right, hopefully you've had a chance to do that. So we can go to our summary output page for the regression analysis. Under regression statistics, multiple R, that's our correlation coefficient. So in this case, it's 0.759. So the correlation coefficient is 0.759, indicating a strong positive correlation or relationship between the number of sales calls made and the number of copiers sold. So Miss Banser is right to stress the importance of making that extra sales call each day. It's not as strong a relationship as we saw in our basketball example, but still a pretty strong relationship here. So, quick note now on correlation and cause. So, high correlation does not mean cause and effect. For example, it can be shown that the consumption of peanuts and the consumption of aspirin have a strong correlation. However, this does not indicate that an increase in the consumption of peanuts caused the consumption of aspirin to increase. Another example is that as the population of donkeys has decreased, there's been an increase in the number of doctoral degrees granted. Once again, we might be able to show that there is a bit of a negative correlation here between those two variables, but it's highly doubtful that the declining donkey population has caused people to go and get their doctoral degrees. So, relationships such as these are called spurious correlations. We do have to just be careful of. So, one thing that can help us here and help us kind of see the causality between the two variables is going to be our coefficient of determination. So the coefficient of determination, r squared, is the proportion of the total variation in the dependent variable y that is explained or accounted for by the variation in the independent variable x. It is the square of the coefficient of correlation, so it will always be positive. So its values are going to range between 0 to 1. It does not give us any information on the direction of the relationship between the variables. We get that from our correlation coefficient. But what it does do is the coefficient of determination tells us a percentage of the variation that can be explained by the relationship between the two variables. So we'll take a look at our basketball example again, and we'll find our coefficient of determination, and then we're going to interpret it. So our basketball example, once again, if you haven't created the table, Just make sure that you go data, data analysis, regression, get this dialog box, make sure it's filled out, hit OK. That'll give you your regression analysis table. For our basketball example, when we look at the table, we're still under regression statistics here. Just below the multiple R or correlation coefficient, you'll see R square, and that's the coefficient of determination. So in this case, the coefficient of determination is 0.819. And so that tells us that 81.9% of the variation in the number of shots made is due to the height of the players. So this shows very strong causality between the players' height and how many shots were made. Basically, what they're saying is the number of baskets made is 81.9% dependent on the height of the player. Now we're going to go to our copier example again. Once again, recommend you pause the video, take a look at your table, see what the coefficient of determination is, and see if you can interpret it as well. All right, so hopefully you've had a chance to do that. We'll go back to our table now for copier sales, and we'll see our R square in this case is 0.576. That's our coefficient of determination. So the coefficient of determination, 0.576 or 57.6%. Sorry, 57.6% of the variance in copiers sold is due to the number of sales calls made. So this shows that there's a moderately strong causality between the number of sales calls made and the number of copiers sold. In other words, there are other factors that go into the number of copiers sold, but 57.6% of the number of copiers sold is dependent on the number of sales calls made. So it's still fairly strong. Um, it's showing strong causality or moderately strong causality. But as a salesperson, if someone goes and tells me that, hey, almost 60% of the number of copiers you sell is going to be determined by the number of sales calls you make, that's something within my control. It's pretty good returns. Probably going to make me want to make some more sales calls. All right, so right before I let you go, we're just going to look at the relationship between the three measures. So there's a relationship among the correlation coefficient, coefficient of determination, and the standard error of the estimate. So the standard error of the estimate and the correlation coefficient are inversely related. That is to say, if the standard error of the estimate is high, the correlation coefficient, let's get rid of that, will be low. Conversely, if our standard error is low, then our correlation coefficient is going to be high. And that should make some sense since the standard error of the estimate shows us how much deviation there is in our data, and the correlation coefficient measures the strength of our relationship. So the less deviation we have, the stronger our relationship is going to be. And then since the coefficient of determination is the square of the correlation coefficient, the higher the correlation coefficient, the higher the coefficient of determination. So the standard error of the estimate measures the variation in the variables. Correlation coefficient measures the strength and direction of the relationship. And the coefficient of determination measures the causality of the relationship. So if we sum up our basketball example, Our standard error of the estimate was 1.89, which is pretty low. And our correlation coefficient is 0.905, which is really high. And our coefficient of determination, 81.9%. So there is low variation in our data, a very strong positive correlation, and 81.9% causality in the relationship between a player's height and how many baskets they made. So this indicates a very strong relationship. For our copier sales, our standard error of the estimate was 9.9, so a little higher. And we can see our correlation coefficient is a little smaller because of that, 0.759, still showing a strong positive relationship. And our coefficient of determination was 57.6%. So there's a moderately low variation in our data, a strong positive correlation, and 57.6% causality in the relationship between the number of sales calls made and the number of copiers sold. All right, that's chapter 12, part B. I hope you enjoyed the lecture. As always, if you have any questions, feel free just to send me a quick email and I will help you out. Take care. Have a great day.